viewers, and welcome to another episode of Space Science with Python. Last time we talked about the Oort cloud and the origin of the long period comets, and today we will take a look at the short period comets, the P-type, and see whether we will find some kind of astro-dynamical parameters or features that help us to distinguish between short period comets or a certain subtype of short period comets and the others. And well, again, this title is a little bit of a spoiler because you will see, or you already see, that it's somehow there are comets that are related to Jupiter. And this relation between certain comet types and Jupiter is indicated by the so-called Tisserand's parameter. So the Tisserand's parameter is something, it's a solution for a three-body problem. So in gravitational theory, if you have three bodies, like here in our case, the Sun, Jupiter, and like a comet, the three-body problem can never be solved analytically, or let's say completely analytically. Always for the orbit prediction, you have to make some numerical analysis, but there are certain, let's say, solution spaces that can be computed. So in our case, we have a huge object, a massive object, the Sun. Another massive object that's, however, which mass is totally way smaller than of the Sun, namely Jupiter. And then a third object, whose mass is, I would say, neglectable. It's a comet. And there's a lot of astrodynamical theory behind it and so on, but this, let's say, it's theory that was being derived by Felix Tisserand was the Tisserand parameter, which is defined here in this equation. And it is a dimensionless number given by this equation. You have the semi-major axis of a planet, in our case Jupiter, the semi-major axis of the minor body, in our case the comet, the inclination of our comet, again the semi-major axis, and the eccentricity of our comet. And depending on the results, so on the number, we can set the object to a certain relation with, in our case, Jupiter. And you already see, I will provide this link to the Wikipedia article because it summarizes it quite well, also in the description. When the Tisserand parameter is between 2 and 3, as indicated here, we have a so-called Jupiter family comet. So this comet is somehow related to Jupiter, so it's occasionally interacting gravitationally with Jupiter. We will also see later an example how this relationship works. And then there are also other definition ranges, like, for example, asteroids, which have a Tisserand parameter usually larger than 3, or the so-called Damoclids with a value smaller than 2. And these Damoclids are associated with highly elliptical, long period objects. So what we expect is that some P-type comets will be Jupiter family comets because they have a small period of less than 200 years. And maybe you recall that the aphelion of most of these objects was at around 5 or 6 AU. So this is also the region where they sometimes meet Jupiter. So let's see whether this is somehow related to this gas giant or not. And so for this, I created a new script, a new GitHub, new folder on my GitHub repository with the title, with the name of today's video title. So the first two cells, import the modules, and here connecting to the database and selecting the P-type and C-type comets. And this time I'm also only considering the eccentricity smaller than 1. Good, so we have a data frame with the C and the P-type. And now it's time to define this function, let's say as a lambda function, to compute the Tisserand parameter of our comets. And first of all, we need to define the semi-major axis of Jupiter. And we can do this by using SPICE. So this time we will use the kernel. Again, a kernel, meta kernel, where we load some information of the planets. And we compute a state vector of Jupiter, and we will use the state vector to compute the orbital elements of Jupiter, and then we will just extract the semi-major axis and use it for our Tisserand parameter computation. So to compute a state vector, let's use some pseudo ephemeris time, assuming that the orbital elements of Jupiter didn't alter severely in the last couple of years. So let's take the 1st January 2000. So this is our ephemeris time. Now we can compute this vector, state vector of Jupiter. The second entry is the light time of the spicy pi function spk geo. So the target is, in our case, 5. The ephemeris time is the sample ephemeris time. We have a reference frame which is ecliptic J2000, and the observer is the solar system barycenter or sun. Let's just take the sun. Now we get the we will get the state vector. We will use the function Osgeld x of spicy pi to compute the orbital elements, and to compute the orbital elements we need also the g times the gravitational parameter times the mass of the sun value. So this is also a function we already encountered in the past. It is the bot VCD function of spicy pi's of spice. So let's say spicy pi dot bot VCD. The body ID equals 10, and the item we need is g times m, and the expected dimensionality of this value is 1. So we get an array, so we can assign this array to an to a float value. This is the first entry, so this should be the g times m value. Let's see, no error, spawned, perfect. Now we can compute the orbital elements of Jupiter. So orb lm Jupiter, already in the cache, of spicy pi Osgeld x. There we have now the state vector of Jupiter, and then the sample ephemeris time, and then the g gravitational parameter times the mass of the sun, not the sum. I just made a typo. Okay. Good. Now we have these values, and we can extract the semi-major axis from the resulting array. So the semi-major axis, let's call it A. Jupiter, given in kilometers, is the orbital element of Jupiter, and it's the second last entry. So, I just restart. No, I wanted to just run all, just be sure everything works. Yeah, this should be the semi-major axis. Now, if we convert it to AU, it should be around 5. So let's see, spicy pi dot convert, and then A Jupiter in kilometers from kilometer to, come on, AU. Let's have a look at the semi-major axis. And it makes sense. It's around 5, so 5.2 in our case. So we have it now, the semi-major axis of Jupiter given in AU. Now we can compute the create a lambda function for the Tisserand parameter. So let's call it Tisser Jup, or with respect to Jup as you like. And it's a lambda function. We will need the semi-major axis of the comet, the inclination, and the eccentricity. The semi-major axis of Jupiter is not an argument. We'll just use it as a parameter because it's steady state. And let's take a look. First, we need to have the semi-major axis of Jupiter divided by the semi-major axis of the comet plus 2 times the cosinus of the inclination. Cosinus of the inclination times the square root of the semi-major axis divided by the semi-major axis of Jupiter times this 1 minus eccentricity squared. So let's see, numpy square root a divided by Jupiter a times 1 minus e to the power of 2. Yeah, so let's take some brackets to be more clear. Okay, with now, let's make a proper line break. Maybe something like this. Okay, so, okay, no errors, perfect. And now we can compute the Tisserand parameter of for our comet, or our comets, the p-type and the c-type. So we define a new column, which is now called, yeah, Tisserand Jup for Jupiter. This is equal to p-type df, and then we apply lambda x, and then we can apply all the values. So it is basically Tisserand Jupiter, and now it's a equals to x, the semi-major axis in AU. No. We have also the inclination, a little bit lost here. Inclination, I think inclination underscore degree. Thank you for the missing autocompletion. And eccentricity. So eccentricity. That's it. And then, of course, along the axis of 1. Let's get a quick check. Yeah, this looks good. Just some sanity check. How the values look like. Looks good. Let's ignore the output for now. And let's apply the same thing also for the C-type comet, just to compare the results later. Why is it C-type is not defined? Ah, okay, this looks a little bit strange. Rerun everything. Okay, no error. Perfect. Now we can use the function we saw last time. We can use the describe functionality for especially for Tisserand. So Tisserand Jupiter.describe, and then we can take a look and see, okay, the mean value for p-type is 1.2. So there are values that are smaller, but again, I said that not everybody will be a Jupiter family comet, so not every p-type comet is a Jupiter family comet, but we see there's a distribution between 2 and 3, so there are actually values in between. Yeah, we can, I think, also compute maybe the percentage of the values between 2 and 3. So let's say percentage p, okay, percentage p-type Jupiter family comets equal to the length, let's say, of is it the length? Ah, yeah, we can take the length, I think. That's okay. Actually, we can also make a group by, but let's not play around too much. P-type Tisserand parameter larger than 2. So let's put it here like this, and smaller than 3. No, not a hard, smaller than 3. So this is the entire length of this array, and we can divide it by the length of the data frame. So let's see. Okay, I should also maybe multiply it with 100 if I want to have the percentage. Yeah, okay, it's not very good now, but it's around 30%, and I'm now a little bit confused. It should be way more. So maybe I did a mistake here in the upper part, and yep, there is the mistake, because it should be higher. I was a little bit confused when I saw the statistics, because it should be more around 2 and not 1.2. And the reason is here, we use the inclination in degrees, but we need it as radians. So this is the point. Now, the computation returns normal values. Everything appears fine. There's no assertion error, nothing. But maybe you heard already that I was a little bit surprised or confused because it didn't really make sense. And it's good that I did check the percentage, because I know it should be around 80. So let's see. And now it makes sense. Okay. Okay, and now we see also here the distribution is more of what I expected. The mean is at 2.7. So you see, even I did this so many times, and yeah, sometimes you just forget the radians, but you get some kind of feeling if something is not 100% right. So yeah, that's why I did also computed the percentage. And good, now I can continue without any headache. Good. I would say we can, for example, also add these values, the Tisserand parameter, into our database. I mean, it's not really required, but we can do this. We can define a new function. So for example, what we could say, we could define a function called add column to tab. Yeah, add column to table, where you then can define a function to add it into the database. Now, I won't do it here now. You will see it later in the final version. If you're interested how it is being done, what you need to do is, first of all, you need to check whether for example, the column is already existing. So we can say we take cur execute, and then you can check the pragma table info of Comet's main, I think was the, and then corp.fetch all. And then you see, I already inserted it in the past. So you have to take care and create a function to see whether a column name already exists or not. Because I was playing already in the background a little bit. Yeah, again, in the final version, it will be there, but that shouldn't bother us now for the video here. So what we can do now, we can do basically the same thing as last time. So we create again a histogram and a kernel density estimator, but now with the Tisserand parameter to get an understanding and feeling of the distribution. So we define now a Tisserand._range, where we say, okay, let's have values between 0 and, I don't know, 5. And we create the p-type Tisserand kernel. So the same thing as last time with the inclination, we do it here again, where we use the stats Gaussian KDE. We use then the p-type df of the Tisserand. There was the, come on, Tisserand Jupiter values. And then we can compute the distribution as well. So p-type Tisserand distribution where we use the kernel and we call the kernel with the array we defined here. And now we simply copy paste it and apply the same logic to our C-type comets. So P becomes the C. Perfect. And now again, we plot it. Yeah, we can do the same thing as last time. I will not recreate the plot again. I have it here already in the cache. So let me just copy paste it. You can, if you followed the last videos, it's familiar for you. We are, doing some plot. We create a plot. We are doing some formatting. We are creating a histogram of the Tisserand parameter for the p-type and the c-type. We add then also the kernel, the KDE distributions. We set the x limit between 0 and 5, and then maybe here I should write dashed. Setting some x labels, and then at the end we also save the figure. But now let's just execute the plot and let's see what happens. We have here now the P and the C type, and as it was stated in the Wikipedia article, well, the Wikipedia article didn't lie to us. We computed the Tisserand parameter, so the astro-dynamical relationship between the P type and the C type with respect to Jupiter. So you can see between 2 and 3, this is the so-called Jupiter family comets. So these, let's say it this way, these objects are dynamically linked or have a relationship with Jupiter. So again, 83% have this relationship of the P-type comets. And the C-type comets, however, you see a lot of them have a value smaller than 2. So they are the so-called Democlids, who are associated with long period high elliptical orbits. So it makes totally sense what we see here. Now the question is, of course, what does it mean that this object is related to Jupiter? Is it entering the sphere of influence Jupiter regularly, or how does it work? And the short answer is yes. These comets they change their orbital elements, especially when they have close encounters with Jupiter. And I would like to show you a video. It's more about cosmic dust signs and so on, but it helps us to visualize how a famous comet changed its orbital elements and let's say orbital elements by having a, let's say, close encounter or relationship, let's call it this way, with Jupiter. And this comet is Churyumov-Gerasimenko. So you maybe remember 67P, Churyumov-Gerasimenko, was the comet that was visited by the spacecraft Rosetta Philae. So there was landing on the comet a few years ago. So it was a really cool mission. And this is now an animation of the comet starting 1954. You see here the comet, you see here the Earth, the Mars orbit, and here's Jupiter. So this is the Jupiter orbit, this is the Saturn orbit. And there will be a close encounter with Jupiter, I think, 1959, I think. And then you will see how the orbit changes and the object becomes a Jupiter family comet with a Tisserand parameter between 2 and 3. So maybe a small exercise for you. Take the data frame and search for Churyumov-Gerasimenko and compute it. And if you also recall the other video with the asteroid encounter with Earth, a sphere of influence, where the orbital elements have been altered by our home planet, you can compute the sphere of influence for Jupiter and see how the orbital elements of Churyumov-Gerasimenko were before this close encounter and whether the Tisserand parameter changed or not. So let's see. Let's turn on the video. So the camera is rotating with the solar system. In the solar system a little bit, you see the stars in the background. Churyumov-Gerasimenko just passed the sun at a very large distance, June 57, and now you see how it approaches Jupiter, so it comes closer and closer. And it has now a close encounter, and you saw how the momentum, the velocity changed, and also the inclination changed. So the inclination before was a little bit higher. Now the comet is more forced into the, or has been forced into the ecliptic plane, more or less. So this is quite interesting because we also saw the distribution of the inclination was closer to the ecliptic plane because, yeah, of this relationship of with Jupiter, because around 80% of the P-type comets have a astro-dynamical link with this gas giant. Yeah, and what you see now is Churyumov-Gerasimenko emitting some dust with every revolution. We will cover also dust topics in the future, and these dust trails are also being altered by Jupiter. It's a quite nice video, actually. I will share it with you also in the description, so take a look at this. But that's basically it for today. We will cover another comet topic also, I think next or in 2 weeks, I'm not sure. Also covering Churyumov-Gerasimenko. And until then, have fun coding, take care, and see you next time.